Hello, in this video we will solve some exercises of the well ordering principle, first principle of finite induction and second principle of finite induction. So we start with the exercise 1, that is, we can write it as a question 1, and the question 1 is, show that there does not exist integer m such that which is greater than 0 but less than 1. So we have to show that there does not exist any integer between 0 and 1. Let's start the solution. Suppose, on contrary, that there exists positive integer between 0 and 1. So we consider on contrary. Okay, let's s is equal to n belongs to the set of natural number such that this n is between 0 and 1. Means we have considered that the n which are between 0 and 1, we collect all these kind of positive integer and we make a set s. Okay, we assume that s is not empty. We have assumed that s is non-empty and say there exists an element m belongs to s. This means because this m belongs to s and s consists of all those positive integers which are between 0 and 1, so this m will be greater than 0 but less than 1. Then by well ordering principle, says that any non-empty subset of set of natural number has a least or smallest element. Okay, by well ordering principle, s has a least or smallest element, say x. Okay, because this x belongs to capital S, so this will be between 0 and 1. And this means whenever we know that a real number which is less than 1, if we take its square, we get even the smaller number. Okay, if we take the square of x, that will be between 0 and 1 again. And since s is the set of all those positive integer which are between 0 and 1, this means x square also belongs to s. But this is a contradiction. X was the smallest element of s, but we have obtained an element which is less than x and still belongs to s. So this is a contradiction. Hence, this set S is empty. So it is proved that there does not exist any such integer which is between 0 and 1. We move to the question number 2. Okay, the statement is use principle of finite induction to prove that 1 plus 2 plus 3 up to so on plus n is equal to n into n plus 1 over 2. It means the sum of first n integer, positive integer, it is n into n plus 1 over 2. Okay. Solution. We suppose that this given condition, or this is Pn, which we have to prove that Pn is true for all integers. Okay. Now we have to prove that Pn is true. So we consider P1. It means wherever it is n in this condition, in this one, we have to replace by 1. So 1 is equal to 1 into 1 plus 1 over 2, which is equal to actually 1 into 2 over 2, and that is 1. So this equation is satisfied. This means the given condition is true for n is equal to 1. Now suppose the given condition is true for k, which means pk is true, which means 1 plus 2 plus 3 up to so on up to k is equal to k into k plus 1 over 2. This is called actually hypothesis. And now we have to show, or we have to prove, that it is true for k plus 1. Now add k plus 1 both sides. What we get is 1 plus 2 plus so on plus k plus 1 is equal to k times k plus 1 over 2 plus k plus 1. Okay. If we just rearrange it, it will be, if you take the LCM, it will be like this. And if we take the common k plus 1 from this term and k plus 1 from this term, we will get the remaining k plus 2 into k plus 1 over 2. And this shows that Pn, because here instead of n it is k plus 1, and instead of n plus 1 it is k plus 2. So Pn is true. This means P of k plus 1 is true, and hence Pn is true for all n greater or equal to 1. Next question is question 3, and the statement is use principle of finite induction to prove that 1 cube plus 2 cube plus so on plus n cube is equal to 1 plus 2 plus so on plus n whole square. Okay. We, for all n greater or equal to 1. Solution. We consider P1, this condition, for n is equal to 1. This means 1 cube is equal to 1 square, and that is true. This means P1 is true. Now suppose Pk is true, that is 1 cube plus 2 cube up to so on plus k cube is equal to 1 plus 2 plus so on plus k whole square. Okay, now add, this is hypothesis. Now add k plus 1 cube both sides of this equation. We get 1 cube plus 2 cube plus so on plus k cube plus k plus 1 cube, which we have added recently, is equal to 1 plus 2 plus so on plus k square plus k plus 1 cube. Okay, we know that the sum of first n integer or sum of first k integer is actually equal to k into k plus 1 over 2, and there is square this one plus k plus 1 whole cube. Okay, and this is equal to k square into k plus 1 square over 4 plus k plus 1 cube, and if we take the LCM, it will be 4 on the denominator, and that is k square into k plus 1 square plus 4 times k plus 1 cube. And if we rearrange it, or we take the k plus 1 whole square as a common, we will get k plus 1 square as a common. We will left with k square plus 4k plus 4 over 4. Okay, and we see that k square plus 4k plus 4 is actually equal to k plus 2 whole square over 4. Alright, and that can be written as k plus 1 into k plus 2 over 2 whole square, and that is actually equal to, this inner part is actually the sum of first k plus 1 integers, this part. Okay, and this can be written as 1 plus 2 plus so on plus k plus 1 whole square, and this means p k plus 1 is true, and hence Pn is true for all n greater or equal to 1. Now we move to the next question, the question 4. Okay, the statement is, use principle of finite induction to prove 1 into 1 factorial plus 2 into 2 factorial plus so on n into n factorial is equal to n plus 1 factorial minus 1. And the solution is, for P1 means for n is equal to 1, this means 1 into 1 factorial is equal to 2 factorial minus 1, which is also equal to 1. So 1 is equal to 1 on both sides. This means P1 is true. Now suppose that Pk is true. That is 1 into 1 factorial plus 2 into 2 factorial plus on k into k factorial is equal to k plus 1 factorial minus 1. And this is the hypothesis. Now we have to show that it is true for k plus 1, so we add k plus 1 into k plus 1 factorial both sides. We get 1 into 1 factorial plus 2 into 2 factorial plus on k into k factorial plus k plus 1 into k plus 1 factorial and equal to k plus 1 factorial minus 1 plus k plus 1 into k plus 1 factorial. Okay, if we take k plus 1 factorial common from sides, from all terms, it will be 1 minus 1 plus k plus 1. And that will be, no, there is some mistake. This minus 1 will remain alone. Okay, and that will be k plus 2 into k plus 1 factorial minus 1, and we know that if we write, for example, 8 into 7 factorial, it is actually 8 factorial. So that will be k plus 2 factorial minus 1. This means p k plus 1 is true, and hence Pn is true for all n greater than 1. And that's all about today's video. So we will see you in the next video. If video is interesting, then please like the video and subscribe the channel.